When most people hear the word trigonometry, they immediately think of right-angled triangles, sine, cosine, and a lot of memorized formulas. But if we only look at it through the lens of a classroom worksheet, we miss the bigger picture. Today we're going to look at why trigonometry is actually the quote, behind-the-scenes engine of the modern world. First, we have to move beyond algebra. In early math, we focus on solving for a missing x in a linear equation. While that is foundational, trigonometry introduces a different kind of logic. It isn't just about finding a missing number on a page, it's about understanding relationships, specifically the relationship between angles and distances. It's the tool that allows us to calculate things we cannot physically measure, like the height of a mountain or the distance between stars. This brings us to our second point. Trigonometry is a mathematical language. It is the specific vocabulary we use to describe the physical world. Whether it's the structural integrity of a bridge, the rotation of a planet, or the way light refracts through a lens, trigonometry provides the syntax. It allows engineers, architects, and scientists to translate physical shapes and movements into precise data that can be modeled and predicted. Finally, let's look at why it's a modern engine. You use trigonometry every single day without realizing it. GPS. Your phone doesn't just know where you are. It uses trilateration, a complex form of trigonometry, to calculate your exact position based on your distance from multiple satellites. Music and sound. Every song you stream is essentially a series of compressed waves. Trigonometry allows us to model these sound waves, record them digitally, and play them back with high fidelity. It is more than just a chapter in a textbook. It is the invisible framework that makes our digital and physical lives possible. The most powerful thing about trigonometry is that it allows us to measure the, quote, unreachable. We don't need to physically touch an object to know how far away it is or how tall it is. The core principle is simple. If you know the length of just one side of a triangle and the measure of one angle, the laws of mathematics allow you to calculate every other dimension with absolute certainty. In astronomy, this is how we first understood our place in the universe. We can't run a tape measure to the moon or a nearby star. Instead, astronomers use the diameter of Earth's orbit as a baseline. By observing how a star's position shifts relative to the background, a phenomenon called parallax, we create a massive triangle that reveals the distance to objects light years away. Closer to home, we use it in geography. If you've ever seen a surveyor on the side of the road looking through a device on a tripod, they are practicing trigonometry. This is how we map rugged mountain ranges, or determine the height of a skyscraper without ever climbing it. By measuring the angle from the ground to the peak and knowing their distance from the base, the height becomes a simple calculation. Finally, in navigation, triangulation is what keeps the world moving safely. Pilots and sailors don't just rely on looking where they are going. They use signals from lighthouses, radio towers, or satellites. By measuring the angles between these known landmarks, they can pinpoint their exact coordinates on a map. This same logic is the foundation for modern GPS, using the unreachable satellites in space to tell you exactly which street corner you're standing on. While triangles are our starting point, the true power of trigonometry is revealed when we look at waves and cycles. In the natural world, many things don't move in straight lines. They move in repeating patterns. By extending the logic of a rotating circle into a graph, we get periodic functions. This is where sine and cosine stop being just sides of a triangle and start being the pulse of modern technology. First, consider sound and music. Every sound you hear is a physical wave traveling through the air. Whether it's a human voice or a digital synthesizer, we model these vibrations using sine and cosine functions. In fact, when you listen to an MP3, your device is using trigonometry to compress and decompress those sound waves. We've essentially turned music into a language of angles and frequencies. Next, we have electricity. The power running through your home is AC, or alternating current. Unlike the flat flow of a battery, AC power oscillates back and forth. If you were to graph the voltage in your wall outlet over time, it would form a perfect sine wave. Engineers use trigonometry to ensure these cycles remain perfectly synchronized. If the math is off, the power grid fails. It is the mathematical heartbeat of our cities. Finally, we see this in medical imaging. Technologies like MRIs and ultrasounds don't take pictures in the traditional sense. They send out waves, either radio or sound, and record how they bounce back. The raw data they receive is a complex jumble of overlapping waves. To turn that data into a clear image of a human brain, we use trigonometric transformations to decode the signals. We are literally using math to see through skin and bone. We've looked at distances and waves, but trigonometry is also a matter of life and safety. As the tagline says, if you want to build something that doesn't fall over, you need trigonometry. This is where math meets the weight of the real world, ensuring that the structures we inhabit can withstand the forces of gravity and nature. In construction, trigonometry is used to determine the critical angles of a structure. Roof pitch. We use the angle $θ to calculate the slope of a roof, ensuring it's steep enough for rain and snow to run off, but optimized for material costs. Staircases. Designing a staircase is a trigonometric puzzle. You have to balance the rise and run to ensure the angle $phi is safe and comfortable for human use. Bridge trusses. Look at the bridge trusses diagram. Engineers use triangles because they are the only geometric shape that is inherently rigid. By calculating the structural load at every joint, we can distribute weight across a bridge so that it can support thousands of tons without buckling. Beyond just building things, we use trigonometry to understand force analysis. In physics, we often deal with forces that aren't acting in a perfectly straight line. To understand them, we have to resolve vectors, which is just a fancy way of saying we split one diagonal force into two parts, horizontal and vertical. Consider the example of pulling a suitcase. When you pull the handle at an angle, you are applying a total force. However, not all of that effort is moving the bag forward. Some of it is actually wasted as a lifting force. Using the formula $forward equals total CDOT cos theta $, we can calculate exactly how much of your energy is actually doing the work of moving you toward your gate. Whether it's a suitcase, a car on a hill, or a satellite in orbit, trigonometry tells us exactly how much push or pull is happening in any given direction. Up until now, we've talked about how trigonometry helps us build bridges and navigate the seas. But if you've ever played a video game or watched a movie with stunning CGI, you are actually watching billions of trigonometric calculations happening in real time. This is the math that allows us to create digital reality. In computer graphics, every character and object exists in a 3D coordinate system. But your computer screen is flat. It's only 2D. Transformation matrices. To make a character move, rotate, or jump, the computer uses transformation matrices. These are formulas filled with sine and cosine functions. They calculate exactly how every point on that character's body should move in space. Projection, the camera frustum you see here, represents the computer's eye. Trigonometry is used to project those 3D points x, y, z onto your 2D screen xy verse. Every time you turn your character in a game, your graphics card is performing millions of these calculations per second, just so the perspective looks right to you. Finally, we look at robotics, where trigonometry acts as the brain of the machine. For a robot to interact with the world, it has to solve two main problems. Forward kinematics. If the robot knows the angles of its joints, theta_1, theta_$2, trigonometry tells it exactly where its hand or end effector is in space. Inverse kinematics. This is the harder part. If the robot wants to pick up a box at a specific coordinate, x, y, z, it has to work backward. It uses trigonometric functions to calculate the exact precise angles its shoulder and elbow joints need to reach to land on that target. Without these calculations, a robot would just be a collection of metal limbs. With trigonometry, it becomes a precise tool capable of performing surgery or building cars. To wrap up, we have to ask, why does this matter to you? Beyond the GPS in your pocket or the bridges you drive across, trigonometry is a fundamental skill for analytical thinking. It changes the way you look at the world, turning chaotic physical systems into predictable, measurable data. The first major takeaway is spatial reasoning. This is the ability to look at a complex system, like the trajectory of a rocket or the vibration of a guitar string, and break it down into its core components. Systems analysis. When we see a rocket launch, we don't just see motion. We see a series of triangles, vectors, and rates of change. Predictability. By using relationships like SOH, CAH, TOA, or modeling frequencies with dollar frequency, F equals n x F $, we can predict exactly where that rocket will land, or exactly what note that string will play. Trigonometry gives you the X-ray vision to see the geometric logic underneath the surface of reality. Finally, trigonometry is the essential bridge to advanced science. You can think of your math journey as a progression. It starts with pure geometry, where we learn about static shapes and fixed angles. It evolves into trigonometric functions, where we use the unit circle to understand rotation, cycles, and waves. And ultimately, it leads to advanced science and calculus. You cannot have modern physics or engineering without calculus, and you cannot have calculus without trigonometry. Whether you are calculating the rate of change with derivatives like $frac, dx sin x equals x $, or finding the area under a curve with integrals like $into x dx equals x plus c $, trigonometry is the language you use to describe a world that is constantly in motion. So the next time you see a sine wave or a right-angled triangle on a worksheet, remember, you aren't just solving for x. You are mastering the foundational code of the universe. You are learning how to build, how to move, and how to understand the very fabric of our modern world.
That brings us to the end of our deep dive into the world of trigonometry. We've traveled from the basic algebra of triangles to the complex algorithms that power our digital world, robotics, and advanced physics. I hope this session has shown you that trigonometry isn't just a hurdle in your math curriculum. It's a vital tool for understanding how our universe operates. When you master these functions, you aren't just passing a test. You're learning to speak the language of modern science and engineering. Thank you so much for your time and your focus today. If you found this breakdown helpful, please make sure to like the video and subscribe to the channel so you don't miss our next session. We have some exciting topics coming up in the next class, where we'll start applying these principles to even more complex systems. Stay curious, keep practicing, and I'll see you in the next lesson.